Okay, let's continue through this. So, we're not going to be focusing on this class. This is not a huge portion of this class, but it's still important to learn about nuclear energy. Before you skip this video, there's more stuff down the line that you do need. We're trying to cover everything. Now, there's two things we can think of when it comes to nuclear energy. The first is fission. That means I take a particle and I break it apart like right here. I have U-235, a neutron smacks into it. That neutron has to have a certain amount of energy, and when it does, it splits and releases a large amount of energy for the amount of mass that is broke apart. And then those neutrons go off and they split more uranium and more and more and more, and if you're not careful, boom, if you are careful, nuclear power. However, that creates radioactive isotopes, which we can deal with. That's not like a horrible thing, and just as a spoiler, radioactive isotopes aren't in barrels with like ooze coming out of them that glows green magically. Sadly not. They're actually usually solid for one, and they're stored in giant casks or usually concrete. So not nearly as fun to look at and not nearly as Simpsons-esque. The second way we have it is with fusion. So fusion is when I take two small nuclei and I put them together. If you're wondering, like, isn't that like breaking the rules? Because I could just fission and fusion and fission then fusion over and over again. No, actually, if I were to put these two together, it would take this much energy, actually it would take more than that, to fuse them back together. So it takes energy to fuse large things together, but fusing small things together actually releases energy. And once again, it's a small amount of energy if you're thinking about what a joule is. But since I can do that a billion times, hopefully, I can produce a massive amount of energy for a small amount of fuel. Now, while that's really, really cool, we haven't really gotten there yet. We've just recently gotten to the point where we can have a fusion reaction that can produce more power than it actually takes to get it started. Because to make these things fuse, I have to push them together in some way, shape, or form. Usually we do that with lasers. We zap them from one direction, we zap them from the other direction, and it pushes them together. We also use that from electromagnetic fields. A lot of things can do it. But it takes more energy than it actually releases currently. And so we're trying to fix that. Now in a lab, we've been able to have a sustained fusion reaction where it's producing more power than it's taking to do it. But that's in a lab. That's not saying that we can scale that up just now and suddenly start powering your house with it. But that's the hope for the future. Okay, now what's much more important to us in this course is mechanical energy. And at the very beginning, remember a few videos ago, I talked about how we don't care just about energy, but specifically what's the change in energy, okay? The change in energy. And so we have a few so far that we've been introduced to. Kinetic and potential. We have mechanical thing, which can be any sort of way that we're getting energy out of our system. And we have this equation right here where we say, okay, this is equal to how much energy I have, mechanical energy I have for a system. This guy you're used to, that's kinetic. This is potential. And then we have this weird one right here. You're like, wait a minute, what the world is this? That is the work of a flow. Technically, the fluid is pushing the fluid in front of it out of the way, and that pressure also is a type of energy that we can use to do useful work. Eventually, this will turn in what's called enthalpy. Nice. That's when we'll have to get rid of the mechanical at that point when we get bringing it in. Enthalpy, you'll learn about it later. Don't worry about it for now. Now, I can also do this over time. So all I did here was just add the m dot. But I've been talking about how we need the change in energy. So if there's a change, I need to take a difference. And so what I'm doing here is I'm saying, okay, I have a point maybe after my engine. So I have fluid going into it. I have some sort of turbine right here that is spinning. I have fluid going out of it. And work is going to be produced. Because that work is produced, I've removed energy. Because energy's been removed, that means there's going to be a difference. So my pressure and my velocity and even maybe the height will be different afterwards. And the amount of work I'm able to produce is going to be based on what that difference is. How much has it changed? How fast is it changing? All of that's important. And if we want to, I can finally say, what is the rate of change by adding that m dot so I can see how much is happening over time. This is kilojoules per kilogram. This is kilowatts. This is power. This is what we care about for many, many systems. Okay, mechanical energy is useful for most flows because a lot of them don't involve significant heat transfer. Like with our earlier example about the river. We had the lake up here, there was a dam, and then water was going out the bottom. There's not really a big change in temperature when I go from up there to down there. There's a lot of potential energy change. There may be kinetic energy change as well, depending on how it's happening. And all of those go into mechanical forms. So understanding how mechanical forms of energy change is important, and also how much that's changing over time so we can get power out of it. Because remember, we care about energy because we're going to power. Why to power? Because we're trying to power something like our homes, our businesses, machines. We understand how we can use heat to do that because that's our primary way of getting power. Okay. Now, I always do this. I just said this right here. So this is a really good example of mechanical energy. I have a turbine. The turbine is transferring the mechanical energy of this flow into power. And as it does that, I can actually see the difference. Now, in this particular case, if I'm looking at it right here, I can see this big height difference. And if I'm taking it with this big height difference and I'm focusing on this point and this point as my two different points, I can calculate how much energy it could get maximum. Now, the pressure here and the pressure here would just be atmospheric. So since the pressure at both those places is atmospheric, the pressure's not changing. Okay, so that gets rid of one term. Here, I'll write it down for you so you can see it. E is equal to P over density plus V squared over 2 plus GZ. Now, if I look at this, between 1 and 4, there's no difference here. So my delta P, I should delta V, and delta Z. There we go. Put the deltas in. That's 0. Also, if I'm looking here and here, 1 and 4, there's no change in velocity. So that's 0. So this is the only guy that's left. Now, I have a second point though. I can also, if I want to, zoom in and look just before and just after the turbine. In this case, I'm going to assume that my velocity is the same in both places. And my change in height from this point to this point is really, really small when I'm talking about a turbine. So what I'll see instead is I'll see a difference in pressure because this turbine is going to be slowing down the flow. Like the pressure here is going to be greater than the pressure right here because this has a whole bunch of water pushing down on it, and afterwards a lot of energy has been lost, and so there's a lot less pressure there because this turbine is kind of taking out some of the pressure. And so I can do this and I'll actually get the same answer. Both of these will give me the same answer just depending on my point of view. So how you look at a problem is very important because you can sometimes make it very simple on yourself or very hard on yourself depending on how you're doing it. Okay, so we're going to be moving on now to energy transfer by heat, but we'll do that in the next video. So thank you for listening. I'll see you all next time. Bye-bye.